Dear students, this is the third lecture on the weldability of the metals, and in this presentation mainly we will be focusing about the weldability of the different kind of the aluminum alloys. So, first of all in this presentation I will be taking up the lamellar tearing, its mechanism and that how can we control it. Thereafter, we will see the weldability of the aluminum alloys and important factors that affect the weldability of aluminum alloys. These will be related with the properties of the material and the welding procedure and the conditions under which welding is to be performed, like the factors affecting the weldability of any metal system, and then the common problems which are encountered during the welding of the aluminum and that dictate significantly its ease of welding, like the solidification cracking, softening of the heat affected zone, porosity inclusions, partial melting zone related problems. So, we will be starting with this one with the lamellar tearing. Lamellar tearing is commonly encountered in the welding of during the welding of the hardenable steels, which are having very limited z direction ductility, means through the thickness in the through thickness directions ductility of the metal is limited, and this mainly happens when when there is a large amount of the inclusions present in form of the lamellars. So, in form of layers or laminates, and these laminates are formed basically in form of the slag inclusions or silicate inclusions or the iron sulphide inclusions, which are rolled during the manufacturing process. So, these laminates, when these are present and when welding is done in the welding is done. So, the setting up of the tensile residual stresses during the welding, especially in the direction perpendicular to the direction of thickness, the decohesion of these lamellars or of the inclusions leads to the development of the cracks, especially in the regions close to the fusion boundary or below the weld zone. So, here since it is mainly encountered in the heat affected zone, so it is a form of HAZ cracking, and it mainly occurs due to the limited through thickness ductility. It is also called as Z direction ductility, and this limited Z direction ductility is caused by the presence of the elongated inclusions, which are formed due to the rolling during the forming process and setting up of the residual tensile stresses due to that differential expansion and contraction during the welding. And this kind of the cracking mainly occurs during the development of the fillet welds or T joints, and primarily it is triggered by the decohesion of the non-metallic inclusions such as silicates and sulphides. To see this areas in which it is mainly developed, so for that we need to see that if this is the base plate and having the inclusions in form of here laminates of the inclusions, and for the welding purpose, when the melting of the fin surface is done, the weld joint is developed like this, and the tensile residual stresses will be set up, and when these stresses act in direction perpendicular to these lamellars, the decohesion takes place. Another possible situation is when these lamellars are present like this near the surface layers, and when the T joint is developed by developing a fillet weld. So, the fillet weld, when it is its size is longer, especially in case when the lag length of the fillet weld is greater than 20 mm, a lot of tensile residual stresses are set up due to the shrinkage of the this fillet portion, and when shrinkage takes place in this fillet portion, this sets up the tensile residual stresses especially in the areas of in the area of region close to the fusion boundary, that is this zone. So, when this zone is subjected to the tensile stresses in direction perpendicular to the direction of thickness, the decohesion of these lamellars takes place and frequently leads to the cracking. So, these cracks basically develop due to the decohesion of these laminates, and this is mainly attributed to the limited Z direction ductility. So, main reason for this is the presence of the high tensile residual stresses, and the limited z direction ductility. So, if we try to reduce, if we try to improve the z direction ductility by reducing the percentage of these lamellars which are especially present near the surface or near the fusion boundary, or reducing the development of the tensile residual stresses. Apart from the limited z direction ductility and the tensile residual stresses, it is also facilitated by the hardened structure which is formed in form of the martensite and the presence of the hydrogen in the heat affected zone. Hydrogen in the HZ further assists in the development of the lamellar tearing. So, in order to avoid both these situations, if the preheating of the weld is done, then it will help in diffusing out the hydrogen present in the HZ, and also it will reduce the formation of the hardened structures like the martensite. So, those are the approaches which can be used in order to reduce the hydrogen content, in order to reduce the hardness, and in order to reduce the residual stresses. So, as far as the development is concerned, it is the limited through thickness ductility and the presence of inclusions and the development of tensile stresses that lead to the lamellar tearing, and it is primarily triggered by the decohesion of these non-metallic inclusions. Apart from those three factors, the presence of hydrogen, preheating and electrode strength affect the susceptibility to the lamellar tearing, because hydrogen assists in development of the cracks. Preheating reduces the cracking tendency because it helps in escaping the hydrogen, it helps in reducing the tensile stress development due to the reduced differential expansion and contraction, and further it helps in forming the soft structures in the heat affected zone. And the tensile electrode strength, if the electrode is of the lower strength is used, then it will be setting up the lower tensile strength, which in turn will be decreasing the lamellar tearing tendency. So, as far as the control of the lamellar tearing is concerned, it is better to control the lamellar tearing. It will be better if the z direction ductility of the metal system is good, which is measured in terms of the percentage reduction in area should be greater than 15, and then effort should be made to control the residual stresses. For that purpose, buttering of the base metal can be done before developing the weld joint using the low strength metal, so that the stresses are localized mainly in the buttered layer, and the heat affected zone is not subjected to the higher tensile stresses. Reducing the lag length of the fillet, this will further help in reducing the extent of contraction, and so the tensile stresses that are being developed due to the differential and differential expansion and contraction. So, the reducing the lag length of the fillet also helps in reducing the tensile stresses. Then reduce the volume of the weld metal being deposited through the suitable joint design. So, any design which is helping in reducing the volume of weld metal design will eventually will be helping in to reduce the magnitude of the tensile residual stresses or stresses that are being developed in the heat affected zone and in the weld area. These are the some of the approaches which can be used to reduce the residual stresses in the weld zone and in the heat affected zone. And the preheating is another commonly used approach which helps in reducing the diffused hydrogen present in the heat affected zone and reducing the tensile residual stresses because of the reduced temperature gradient from the fusion boundary to the heat affected zone, and further it avoids the hardening of the heat affected zone because of the formation of the soft phases like bainite and the perlite. So, these are some of the approaches which can be used to reduce the cracking tendency, means the lamellar tearing tendency of the steel weld joint. Now, we will be taking up the weldability of the aluminum alloys. In general, aluminum alloys are considered to be difficult to weld as compared to that of the steels, and the reason for this difficulty in welding of the aluminum is that it has high affinity to the oxygen, it offers the higher thermal expansion coefficient, and the thermal and electrical conductivity of the aluminum is high. These are the very three key properties that significantly affect the weldability of the aluminum. So, if you want to assess the weldability of aluminum in the same line of the weldability of any metal system, we need to see that how what kind of the weld joint can be performed when it is welded using a given process, using a given set of the procedures for a given purpose and the fabrication, and in a given set of the fabrication conditions. So, we know that if we steel is welded using this SMAW process, we can get the reasonably good quality weld, but when SMAW welding is used for aluminum welding, we find a very poor quality weld joint. So, we need to put in more efforts and more skill for developing the weld joint of the aluminum alloys, and that those efforts will be in form of use of like inert gases for protecting the weld pool from the atmospheric contamination, or use of the tungsten electrode or the gas metal arc welding processes, which offer higher energy density for melting the fin surfaces of the aluminum alloys, because it is of the higher thermal conductivity. So, again to assess the weldability of aluminum alloys, we need to see that what quality of the weld joint will be produced using a given process, and how that particular weld joint can be used for a given purpose, and with the change in condition there will be great change in the weldability of the aluminum alloys, and the fabrication conditions under what the weld joint is to be developed. Weldability of aluminum may be poor, and when welded using the SMAW process or the gas welding, and because of this is because of the high affinity of the aluminum with the atmospheric gases like oxygen. So, when the aluminum reacts with oxygen, it forms the refractory aluminum oxide, and this it is found very difficult to melt this, and the presence of the aluminum oxide reduces decreases the melting, means imposes difficulty in melting of the aluminum. At the same time, if it is present in the weld, it will be acting as a inclusion. The weldability of the aluminum is this is one of the reasons because this is one of the reasons because of which it is found difficult to weld aluminum by the SMAW process or the gas welding. The same may be, but the weldability of the aluminum may be very good when some tungsten inert gas welding process or the gas metal arc welding process is used, because the presence of these inert gases for protecting the weld pool from the gases present in the atmosphere help in developing the sound weld joint, and which can serve the purpose of getting the weld joint which can take up the service load as per the purpose or as per the intended application. Similarly, so that was the effect of the process. Process significantly affect the weldability of the aluminum. It may be very poor with the SMAW and GMAW, it may be very poor with the gas welding, but the weldability of aluminum may be very good with the GTAW and GMAW processes. Similarly, the welding procedure significantly affect the weldability of aluminum alloys. For example, edge preparation, if the edge is being prepared properly, means proper cleaning is being done to remove the aluminum oxide. The welding procedure parameters are being used, like the proper welding speed and current are being used for ensuring the proper melting of the fin surfaces in order to develop the weld joint. And if the welding current is low, then due to the high thermal conductivity, it may be difficult to weld, it may be difficult to melt the fin surfaces of the aluminum. Then the welding consumables, like the use of the welding consumables in some of the cases, like use of aluminum magnesium as a filler, causes the tendency of the solidification cracking, causes the solidification cracking tendency, while the use of the aluminum silicon filler sometimes decreases that the solidification cracking tendency. Similarly, the use of the argon results in the weld joint which is comparatively of the poor quality as compared to the case when the helium is used, or we can use the mixture of the argon with the oxygen or with the hydrogen, and similarly we can use the carbon dioxide with the hydrogen. So, the presence of means the change in the shielding gas will be affecting the protection being provided by these gases to the weld pool from the atmospheric contamination, and accordingly it will be affecting to the quality of the weld joint which is being produced. And then preheat. preheating will be affecting the width of the heat affected zone. So, it may, in case of the aluminum alloys especially, it will be leading to the increased softening of the heat affected zone, and the kind of post weld heat treatment is being used, whether we are using the stress relieving treatment, or the treatment is of the solutionizing kind, or it is the T6 or the T4 kind of heat treatment is being used. Accordingly, the properties of the weld joint will be affected significantly. So, depending on the procedural steps which are being used for developing a weld joint weld joint of the aluminum alloys, we may get a wide range of the weldability, or the degree of weldability may vary significantly according to the combination of the procedural steps which are being used for development of the weld joint. Then the properties of the aluminum alloys that affects its weldability, and which because of which it is found of the lower weldability than the steels. So, the main reason for the poor weldability of aluminum as compared to that of steel is the high affinity of the aluminum towards the atmospheric gases. When the aluminum reacts with oxygen, it forms the refractory alumina, and this is most of the time is present as an inclusion in the aluminum weld joint, which in turn decrease the mechanical performance, because these provide easy site for stress concentration and easily nucleate the crack, and their growth is facilitated. High thermal expansion coefficient, the thermal expansion coefficient of aluminum is higher than the steel, and because of this it is subjected to the greater expansion and contraction during the welding, and increased expansion and contraction during the welding leads to the greater the development of the residual stresses, and because of which increased tendency of the distortion and the cracking of the aluminum weld joint, especially from the heat affected zone, and the partial melting zone, means from the and from the heat from the weld zone. So, increased magnitude of the residual stress in the weld region will be promoting the cracking tendency in some of the aluminum alloys from the weld region and in the heat affected zone. Then the high thermal conductivity and electrical conductivity, because of the ability of the because of high thermal and electrical conductivity of aluminum alloys, these will be extracting the heat very rapidly from the weld region, and this because of this melting of the aluminum alloys may be more difficult as compared to that of steel, and because of this we require the welding process of the higher energy density, and higher current levels are required to bring the aluminum alloys to the molten to achieve the melting in the aluminum alloys in order to develop the weld joint. Similarly, electrical conductivity plays a big role in spot welding of the aluminum alloys, because of the high electrical conductivity it decreases the electrical resistance heating and the heat which is being developed at the interface. So, because of this it requires a higher level of the current setting for developing the spot welds in the aluminum alloys as compared to that of the steel. Then the poor rigidity, aluminum is not considered to be that stiff and rigid because of this poor rigidity when it is subjected to the residual stresses during the welding. This leads to the easy distortion, and in order to take care of this it is required that proper preheating is done, and at the same time high energy processes are used, so that the sound weld joint can be developed without the problem of distortion. And then high solidification temperature range, most of the aluminum alloys in most of the aluminum alloys, when addition of the alloying element is done, the solidification temperature range increases, and this increase in solidification range increases the tendency of the solidification cracking, and the cracking in the partial in the cracking in the heat affected zone due to the partial melting effect in some of the areas especially close to the fusion boundary. These were the some of the characteristics related to the aluminum alloys that affect the ease of the welding of the aluminum alloys significantly. So, we have seen that there are various characteristics of the aluminum alloys which impose difficulty in welding. So, in order to take care of the above characteristics, so that the sound weld joint can be developed, basically two types of approaches are used. One, that effective protection of the weld pool from the atmospheric contamination, so that and for this purpose helium and argon gases are used to seal the weld pool from, so that the effect of the atmospheric gases onto the weld pool can be reduced. And another is since most of the problems are related with the differential expansion and contraction and the differential weld thermal cycle being experienced by the aluminum alloys during the welding. So, in order to reduce the effect of the weld thermal cycle on the properties of the weld zone and the heat affected zone, it is desired that the heat input is given as less as possible, and for that purpose high energy density processes like the GTAW, electron beam, laser beam are used, and in the same line arc pulsation can also be used. So, pulse tungsten inert gas welding, pulse GMAW processes, electron beam will be helping in this regard significantly in order to reduce these will be helping significantly in reducing the amount of heat that is being supplied during the welding, and because of which it will be reducing, these will be reducing the adverse effect of the weld thermal cycle in the properties of the weld region and the heat affected zone. So, basically these are the two approaches which are used to take care of the negative aspects related to the welding of the aluminum alloys, like effective protection of the weld pool and reducing the heat input which is being given by using the higher energy density processes. So, these two approaches basically work on the protection of the weld pool, mainly the protection of the weld pool approach mainly deals with the using various environments such as vacuum, helium, argon or the mixture of these gases with oxygen and hydrogen to seal the weld pool, so that the adverse effect of the atmospheric gases on the weld pool can be reduced. And the another is that the reducing the influence of weld thermal cycle, it has led to the development of the newer processes such as the laser pulse variant of the GTA and GMAW, and the solid state processes like the friction stir welding of the aluminum alloys. The friction stir welding of the welding has been very extensively used for the welding of the aluminum alloys because it is performed in the solid state. This process has been developed recently in by the TWI in 1991. In this in this process the melting of the aluminum is not required, but using the frictional heat and the deformational heat, the material is softened, and then using the mechanical forces consolidation is done between the components to be joined of the aluminum alloys. So, melting is not required, and because of this avoidance of the melting, the weld joint which are produced by the friction stir welding process of the aluminum alloys, the quality of the weld joint is found to be very good, and the lot of research is still being done on the weldability or of the aluminum alloys using the friction stir welding process. Now, as far as the factors that decrease the quality of the weld joint of the aluminum alloys and which in turn will be affecting the weldability, we need to see that what are the undesirable features that are commonly developed during the welding of the aluminum alloys. These include the porosity cracking, which is in form of the solidification cracking and the liquefaction cracking. Solidification cracking will be occurring in the weld region, and the liquefaction cracking will be taking place in the heat affected zone. Then inclusions primarily due to the formation of the aluminum oxide and the softening of the heat affected zone. This happens mainly due to the grain growth in the heat affected zone, and the reversion of the hardening precipitates in the heat affected zone, and the coarsening of the hardening precipitates in the heat affected zone, especially in case of the precipitation hardenable aluminum alloys. While the softening in case of the work hardenable aluminum alloys like 5000 series aluminum alloys 5052 or 5086. In these aluminum alloys, basically softening occurs due to the recovery and recrystallization effects of the weld thermal cycle, and the distortion is the another problem which is which decreases the weldability of aluminum alloys, and it is common in aluminum alloys because it offers a higher thermal expansion coefficient, and high thermal expansion coefficient associated with the welding increases the tendency of the differential expansion and contraction, and which in turn increases the tendency of the distortion. So, now each of these problems will be discussed one by one, and what can be done in order to overcome them. Inclusions are formed in the welds of the aluminum alloys mainly due to the presence of the foreign metals foreign constituents like these may be impurities, or these may be in form of gases, or these may be in form of thin films and the solid particles. The inclusions in case of the aluminum welds are mainly found in form of the hydrogen gas and the aluminum oxide as a solid particles. So, if any foreign material which is not expected to be there, if it is present, can be considered as inclusion, and these inclusions may be in form of gases, thin films and solid particles. So, the main causes of the inclusions include like a high affinity of the aluminum with the atmospheric gases increases the tendency of the formation of oxides and the nitrides, because these are of the densities similar to that of the aluminum, and because of having the similar density as compared to that of the aluminum, these tend to remain in the molten weld pool, and because of that they do not come up to the surface in form of the slag or in form of impurities, and because of because of this region these tend to be there in the weld region. So, the main reason behind the presence of the aluminum oxides and aluminum nitrides in the weld is that if the reaction between the atmospheric gases and the aluminum is taking place, it will forming oxides and nitrides which will have the density similar to that of the molten aluminum, and they will have the tendency to be there, and they will not be able to float on the surface of the molten metal, and because of this the entrapment tendency of these in oxides and nitrides in the weld region increases, and these are caused and when these reactions take place, the main the things which promote the formation of the oxides and nitrides during the welding of the aluminum alloys include the inefficient protection of the weld pool. Means the whatever the method is being used to protect the weld pool, whether it is vacuum in case of electron beam welding, or it is the shielding gas which is being used not being in the same amount which it should have been, means the gas flow rate is limited or excessive and the movement of the arc during the welding. So, all the factors that are affecting the protection of the weld pool, they will be increasing the possibility of the inclusions, and improper cleaning of the filler material and the base material. If these have not been cleaned properly, then the impurities may be in form of the hydrocarbons which will be offering the hydrogen and carbon during the welding on decomposition, and then the shielding gas itself is impure. So, it will be providing the oxygen and hydrogen which will be reacting with the aluminum to form the aluminum oxide, as well as hydrogen will be increasing the hydrogen induced cracking in the aluminum, hydrogen induced porosity in the aluminum weld. Then the presence of gases in the dissolved state in the base metal itself, like gases like the hydrogen or oxygen, if these are already present in the base metal, then these will be promoting the hydrogen induced porosity and the aluminum oxide inclusions. And the tungsten inclusions are formed when the tungsten inert gas welding process is used, and commonly the pure tungsten electrode is being used. So, when the tungsten is used for pure tungsten is used as an electrode for the tungsten inert gas welding process. This tungsten due to the heat of the arc is degraded and decomposed, and sometimes it is transferred to the weld pool, and when it is transferred in form of the small pieces, it leads to the development of the tungsten inclusion in the weld in the aluminum weld. This is and the tungsten inclusions are formed mainly in case when the touch start method is used, or very inappropriate the welding current, and the polarity is being used for the tungsten inert gas welding process. So, in order to control the inclusions to reduce the formation of inclusions in the weld, effort should be made to protect the weld pool from the atmospheric gases properly. So, for this purpose, shielding has to be done properly with the required flow rate and the correct kind of the gas and its grade. Avoid the formation of the tungsten inclusion. For this, we need to see that the proper current setting is used for a given electrode size, and the proper kind of polarity is used in order to avoid unnecessary degradation of the tungsten electrode. And further, the proper welding procedure should be established, so that we select the proper kind of electrode, suitable welding parameters are used, and the correct kind of shielding gas is used, and the arc is manipulated properly, so that the unnecessary the presence of the gases in the arc zone is avoided, and the tungsten degradation of the tungsten and its decomposition is reduced during the welding, especially in case of the tungsten inert gas welding process, and the desired purity of the shielding gas is also ensured, so that these gases means oxygen, nitrogen, or the hydrogen gases are not present with the shielding gas which is being used for to protect the weld pool. So, these are some of the steps which can be used to control the inclusion formation in the weld joint of the aluminum alloys. The solidification cracking is another common type common type of the problem which is encountered during the welding of the aluminum alloys, mainly in case of the aluminum copper alloys, aluminum magnesium silicon alloys, and aluminum zinc magnesium alloys, and this is mainly happens due to the two regions that the tensile residual stresses develop at the weld center, and the properties of the weld metal are poor, especially at the high temperature. So, the poor properties of the weld metal at the high temperature are basically because of the filler material and the weld metal characteristics which are being used, and the differential expansion and contraction of the weld metal is attributed to the development of the tensile residual stresses in the weld zone, and this kind of the cracking is observed mainly along the weld center line due to the setting of the tensile residual stresses, especially in the aluminum alloys which offer the higher solidification temperature range. We have seen that there are two main factors. One is the setting of the residual stresses, that is the tensile residual stresses, and the second is poor mechanical properties of the weld at the high temperature. If the poor properties of the weld metal at high temperature in form of limited ductility, low strength, then under the tensile residual stresses weld metal tends to crack. So, it is desirable to have the reduced magnitude of the tensile residual stresses being set up in the weld zone. At the same time, the weld metal is having the reasonably good ductility and the strength even at the high temperature. So, the following factors affect the contraction of the weld, and so the residual stresses, and which in turn affect the solidification cracking tendency. One is the thermal expansion coefficient of the weld metal and base metal. In general, higher is the thermal expansion coefficient, greater will be the residual stresses, and so there will be increased solidification cracking tendency. Then the melting point, if those aluminum alloys having the if melting point of the filler metal and the base metal and the relative values of the each, say if the solidification of the weld metal is taking place the first, then the whole of the weld metal will be solidifying first. So, in order to avoid this the solidification cracking tendency, it is necessary that the melting point of the aluminum alloys is not over a wide range, but the range of the temperature over which solidification of the weld metal takes place, it is very narrow, and because of this most of the weld metal will be solidifying under the very short range of the temperature, and largely at the same time, and because of this most of the residual stresses being set up will not be localized along the weld center line, and that is why how it will be helping to reduce the solidification cracking tendency. Then the weld bead profile affects the weld bead profile also affects the setting up the residual stresses. For example, convex bead promotes the solidification cracking tendency, while the concave bead promotes the solidification cracking tendency in case of fillet weld, while convex bead reduces this kind of cracking tendency. In the type of weld and the degree of constraint and the thickness of the workpiece. So, increased degree of constraint, increased thickness will be promoting the residual stresses, and so the cracking tendency of the weld. So, as far as the properties of the weld metal and solidification cracking tendency is concerned, the low strength and the low ductility weld metal, especially in the last stage of the solidification, significantly increase the solidification cracking tendency, and therefore, efforts are always made to have the reasonably good strength and ductility even at the high temperature near the end of the solidification stage. However, these properties are affected by the many metallurgical factors, and the metallurgical factors that are affecting to the solidification cracking tendency are many, like the composition of the weld metal, the microstructure, segregation tendency, solidification temperature range, fluidity of the low melting point phases being formed in terms of the surface tension and the viscosity. So, these are the factors that significantly affect the solidification cracking tendency, and one by one these will be taken up. So, as far as composition is concerned, the presence of all alloying elements like silicon, copper, magnesium, zinc that increase the solidification temperature range tends to increase the solidification cracking tendency also. So, in general, addition of these elements in aluminum first widens the solidification temperature range, and then after reaching to the maximum it decreases gradually, and because of this also, when the aluminum alloying addition is done in aluminum, these increase the solidification cracking tendency first, and after reaching to a maximum value the solidification cracking tendency starts to decrease, and this happens mainly because of the first increase in solidification temperature range, and thereafter after reaching to the maximum value it decreases gradually. For example, if we see here, this is the liquidus line and this is solidus line in case of the aluminum silicon phase diagram. When aluminum is pure, it solidifies, means the melting and the solidification temperature is 1, and that is around 662.5 degree centigrade, and with the addition of the silicon we can see there is the range of the solidification temperature keeps on increasing, and for about say 1.65 the solidification temperature range is maximum, and thereafter it starts decreasing because the solidus and liquidus temperature keeps on coming closer. So, at this value means for 11.7 and for the pure aluminum, whole of the solidification will be occurring at one temperature, while for 1.65 the solidification will be occurring with the maximum solidification temperature range. So, for this kind of composition the cracking tendency of the aluminum silicon alloy will be maximum, while it will be nil for the pure aluminum and for the eutectic aluminum alloy system. So, if we see that how the variation in cracking tendency takes place with the change of composition. So, for the silicon it is around 1.6%, for aluminum copper it is around 4 to 6%, and then for the magnesium again it is around 1 to 2%, and for the magnesium and Mg2Si, it is a kind of intermetallic compound. For this kind of the variation in the concentration of the Mg2Si around 1% its maximum, then it starts decreasing. So, when we have the large amount of the low melting point phase, then it fills up the region which is being cracked, and because of this the cracking tendency is found the on the lower side when the concentration of the alloying element is significant. So, but in all the cases with the addition of the small amount of these alloying elements, the cracking tendency in all the cases can be seen that it increases with the addition of all these alloying elements, and after reaching to the maximum it starts decreasing, and keeping these concentrations of the silicon, copper, Mg2Si, the suitable filler material is selected during the welding of the aluminum, so that we are not in the crack sensitive zone, but we are in the safer zone. So, the safer zone, again this is the safer zone for the aluminum silicon system, this is the safer zone for the aluminum copper, for aluminum magnesium this is, where cracking tendency is minimum. This is for Mg to Si. So, filler material is selected in such a way that we are in the safer zone where cracking tendency is minimum. So, the concentration of the alloying element in the weld metal, so the filler metal is selected in such a way that we have the weld metal composition corresponding to the minimum solidification temperature range or corresponding to the minimum cracking tendency zone. And for this purpose only the two types of the filler materials are commonly used, where aluminum 5% magnesium is used or aluminum 5 to 12% of the silicon is used. Use of the aluminum 5 to 12% of the silicon significantly decreases the solidification cracking tendency in the welding of the aluminum alloys, and therefore, aluminum silicon filler metals are commonly used during the welding of aluminum alloys. Now, we will see the effect of the grain structure on the solidification cracking tendency. We know that if the grain structure is fine and equax, it will provide the better flow of the liquid metal available for healing the cracks which are being developed due to the localization of the tensile stresses. So, this the fine equax grain structure will provide the better healing of the incipient cracks through the backfill by the liquid metal available at the last stage to solidify, and conversely for a given solidification cracking sensitivity alloy, if we are having the columnar grain structure, then the cracking tendency will be more as compared to the case when we are having the fine equax grain structure. And the reason for this is that when we are having the coarse columnar grain structure, there will be more segregation of the alloying elements along the weld center line, which will be increasing the cracking tendency, especially along the weld center line, because the grains will be abutting at the weld center line, and that will be pushing in the alloying elements along the at the weld center line. Say if we are using the low welding speed, we will be having the elliptical weld pool and the grains will be curved, and will at the same time we will be having axial grains. In this case, the concentration of the alloying elements will be distributed in better way as compared to the case when we are using the higher welding speed. At higher welding speed, most of the grains will be columnar, and this will be pushing in the alloying elements along the weld center line, and which in turn will be increasing the cracking tendency. So if we are having the finer equax grain structure, that will have the minimum cracking tendency as compared to the case when we are having the coarse columnar grain structure. Then the morphology of the low melting point phases. Many low melting point phases are formed during the welding of the aluminum alloys and the steels also. So, in case when the low melting point phases are present in form of thin films, this kind of the morphology is more sensitive towards the solidification cracking as compared to the case when the low melting point phases are present in form of the globules. And because of this, thin films like morphology of the low melting point phases is formed when the viscosity and the surface tension and viscosity of the liquid metal lost to solidify is very low, and this results in the higher solidification cracking tendency as compared to the case when the low melting point phases are formed in form of the globular morphology. So, then the refinement of the grain structure is the approach which is used to control the solidification cracking tendency. We have seen that the coarse columnar grains increase the solidification cracking tendency. So, refinement of the grain structure especially with the equax grains helps in developing the resistance to the solidification cracking tendency significantly. So, the refinement of the microstructure of the weldment can be achieved using the various approaches like the inoculation, where the grain refiner is added from outside, which can act as a nucleant to refine the grain structure. Use of the external force like the electromagnetic forces or mechanical force in form of mechanical vibrations. These methods are basically used to create the disturbance in the weld pool, so that the dendrite fragmentation and grain detachment can be obtained in order to produce a large number of nucleates in the weld pool, so as to refine the grain structure, and further reducing the heat input, so that the high cooling rate can be achieved in order to obtain the finer grain structure, and this is done by adjusting the welding parameters in such a way that the heat input can be reduced, and for this V and I are reduced, the heat input is reduced and the welding speed is increased. Then another approaches of reducing the solidification cracking tendency is reducing the tensile residual stresses, and for this purpose the weld stress relieving treatment can be done just after the welding, and the mechanical methods like the short peening and the short blasting can be used in order to have the localized deformation at the surface, so that the development of the tensile residual stress can be reduced, and the controlling the weld bead geometry like having the concave weed means the convex weed can be developed in place of the concave weed, which will be reducing the solidification cracking tendency because of the setting up of the compressive stresses, especially at the surface. Now, softening is the another effect related with the welding of the aluminum alloys, which is observed, and it adversely affects the weldability of the aluminum alloys. Softening of the heat affected zone is observed in both kind of aluminum alloys, either they are of the precipitation hardenable or work hardenable. Precipitation hardenable aluminum alloys like the aluminum copper system, aluminum zinc magnesium, aluminum magnesium silicon systems. In these systems basically when the exposure of the heat is given during the welding, whatever hardening precipitates are there, they tend to get dissolved in the aluminum matrix, and the dissolution of the hardening precipitates decreases the hardness, and this phenomena is called a reversion of the hardening precipitates. And apart from the reversion, the coarsening means the hardening precipitates tend to coarsen due to the overexposure of the heat affected zone to the thermal weld thermal cycle or the heat which is being applied during the welding. So, coarsening of the precipitates also decreases the hardness of the aluminum alloys, especially in the heat affected zone, and the work hardening aluminum alloys are also subjected to the softening because of the recovery and recrystallization effects. During the recovery, basically the dislocations will be decreased significantly, and by the recovery fresh grain structure, and by the recrystallization fresh grains will be formed, which will be decreasing. So, recovery and recrystallization both will be decreasing the hardness because of the elimination of the work hardening effect, and apart from the recovery and recrystallization, coarsening of the grain structure in heat affected zone also decreases the hardness. So, whether it is the work hardenable aluminum alloy or the precipitation hardenable aluminum alloys, in both the cases the softening of the heat affected zone will be taking place, and that will be weakening the weld joint, and frequently it becomes the zone where from fracture can take place under the tensile loading or under the fatigue loading conditions, and therefore, to avoid the adverse effect of the softening of the heat affected zone, the precipitation hardening treatment is done after the completion of the weld joint. Now, I will summarize this presentation. In this presentation, first of all, we saw the basic mechanism contributing towards the development of the lamellar tearing and the approaches which can be used to control the lamellar tearing. Thereafter, we have seen the factors that affect the weldability of aluminum alloys and important the problems which are encountered during the welding of aluminum alloys and what can be done in order to control them. Now, in the next presentation, that will be the last presentation on the weldability of aluminum alloys. Mainly we will be talking about the failure analysis approach which is used to establish the cause of the failure of a particular component. Will be supporting those means the failure analysis and prevention of the weld joint will also be taken up with some examples. So, thank you for your attention.